Okay, so hello everyone. Welcome to the talk. I'm Xinran from University of Southern California. Sorry that you have to listen to another talk with exactly the same title. But this is joint work together with David Kempe, also from USC. So let's start. So I think we have already proved to you that diffusion is really an interesting and fundamental phenomenon in the study of social networks. Actually, different kinds of things, for example, news, idea, information, innovation, the adoption of product, and even rumor can propagate in the network. So here's one example. Assume that one user just bought a nice new phone. He may influence his friend into buying the same type of phone. Now his friend himself also has this phone, may influence his own set of friends. Actually, this process could go on and on in the social network, and eventually a lot of people will end up buying this new phone. So to be more precise, in the previous example, it actually follows from one of the most widely used diffusion model, that is the independent cascade model, or in short, the IC model. Under this model, each newly activated node U will have a single chance to activate each inactive neighbor V with probability PUV, and we call them the activation probabilities. So of the many applications of the diffusion behavior in social networks, probably the most famous one is wherein marketing. Basically, a company could utilize the diffusion behavior to promote its new product among the individuals in a social network. The way it achieves so is to give some free samples of your product to some of the individuals in the network in order to trigger a cascade as shown in the previous example. Then it naturally comes with the algorithm problem of influence maximization, that is, which set of the individuals the company should choose to give them the free samples. This problem is first formulated by Kempe et al. In 2003 in KDD. It focuses on finding a set S of at most k people that maximize the value of influence function. The value of influence function sigma is simply the expected number of people that are activated by the end of the diffusion process. Since the proposition of this problem, numerous algorithms have been proposed solving it with or without approximation guarantee. However, if you would like to apply any of such algorithms for a real-world wherein marketing campaign, you have to answer the following question first. That is, where does the influence function sigma come from? Because in most cases, they're not directly observable. In many cases, you can only observe the structure of the social network. But it's very hard for us to decide which diffusion model, if any, best captures the diffusion process in the real world. So in many cases, we have to make our best guess or simply assume one of the most widely used ones. For example, here, let's assume that we use the independent cascade model. After the modeling assumption, we can either collect some diffusion occurred previously on the network, or maybe use the old-fashioned way to run questionnaire to obtain the parameters associated with the diffusion model. For IC model, there are the activation probabilities. Since now we have our model assumption and the inferred parameters, we have our influence function, namely the objective that we try to maximize. Then we can apply any of our favorite influence maximization algorithm to select our seeds. A simulation shows that our selected seeds can successfully activate a lot of individuals in the network. So it seems that we get a pretty good solution, and it seems that problem is solved. But perhaps let's wait for a second. As mentioned in Wei's talk, sometimes we can't be sure that we estimate all the parameters correctly. Or things could be even worse. How could we be sure that we choose to use the correct diffusion model? Perhaps in real world, the diffusion process may follow from another model. Say, for example, the linear threshold model. As we select our seeds solely based on the assumption of the independent cascade model and the associated parameters, and then our select seed may perform really badly if the ground truth diffusion process follows from the LT model. Say, for example, here, it could only activate 2 nodes. Or maybe in real world, the diffusion may follow from the continuous time extension of the independent cascade model. Under this case, similar situation happens, and our node may perform really badly. So this example shows that there are actually a lot of uncertainty when we try to choose which influence function to maximize. And actually, choosing the correct one is really vital for the success of wherein marketing. And in the previous slides, we mentioned about 2 possible sources for this error when we choose which influence function to maximize. One is misestimation of this model parameter, as mentioned by Wei in his previous talk. Another source is the misspecification of diffusion model. But sometimes there are other factors as well. Sometimes when we want to maximize influence over a dynamic network, then we need to decide based on which period of the network that we should maximize our influence. Or we could have topic-specific networks, as we know that the strength of influence between individuals really depends heavily on what kind of topics is under propagation. To make things even more complex, actually the combination of each of these factors will contribute to us a distinct candidate influence function. For example, if we use the assumption of IC model for dynamic network at July 2016, and for the topic music, we will have one influence function, for example, sigma IC, July, and music. If we can be sure that this is the ground truth influence function, then we can do a good job of maximizing the influence on it due to the development of many efficient influence maximization algorithms. But usually, we can't be sure of that because there are many other possible candidates. For example, another candidate could come from the combination of LT model, August, and sports, or the candidate could be the combination of CIC model, June, and sports. Since we select our Cs here only based on the influence function in the middle, if either the left candidate or the right candidate is the ground truth influence function, then our Cs will do a pretty bad job. That is something we don't want it to happen. Then how could we possibly to improve this solution? So perhaps instead of just focusing maximizing one influence function and pretending it as the ground truth one, let's simultaneously try to focusing on all possible candidates and try to select Cs that are guaranteed to be good for all of these candidates. So if we have that in our mind, perhaps we want to choose this node, as we see this node can consistently activate two individuals, no matter which candidate is the ground truth one. And that is exactly the goal we try to achieve in our paper. Basically, we want to find a set of Cs that are robust to multiple diffusion settings. One diffusion setting is just one influence function that we may want to maximize. In our case, different from Wei's previous talk, we assume that the set of influence functions forms a finite set, and we assume that this set is given as input to our algorithm. We refer our goal as robust influence maximization, which takes the form of the following optimization problem. So let's try to pass it in detail from right to the left. So the right part, which is called the robust ratio, as mentioned in Wei's talk, basically the denominator gives the influence of the C set you select, while the denominator is the optimum influence that you could possibly achieve under this influence function sigma. The fraction here gives that what percentage of optimum can you achieve by your seed. If you ignore the other part, maximizing this ratio is equivalent to the original influence maximization problem. The interesting part comes from the middle, where we take a minimum over all possible candidates. The rationale behind this is that we don't know which candidate is the ground truth one, so we want to select our Cs to guarantee that it works even for the worst candidate. Finally, we have this maximization, as in the original influence maximization problem, which we want to select the C set subject to the cardinality constraint. Okay. So now we have formulate our problem. Let's think about how we can actually solve it. So in our work, we call the robust ratio as ρS, which is our objective for robust influence maximization. So actually, this problem is quite challenging to solve. The first challenge comes from the fact that our objective may not be efficiently computable because the denominator in the robust ratio actually involves the optimum solution of influence maximization, which is known to be NP hard to compute. However, this challenge is easy to handle. We can simply replace the optimum influence to that obtained by the greedy algorithm. As we know that greedy algorithm provides us a 1-1/E approximation guarantee for the optimum influence. By doing so, we only lose a multiplicative factor of 1-1/E, and we can live with that. The real challenging part comes from the following fact. That is, our objective is no longer submodular. We see that a set function is submodular if it satisfies the following diminishing return property. And good thing about submodular function is that we can maximize its value using this simple hill climbing greedy algorithm to obtain a constant approximation guarantee. But unfortunately, that is not the case for our problem. Instead, our objective is the minimum of many submodular functions, which are not necessarily submodular itself. And in our work, the way we handle this challenge is to adopt from a previous algorithm by Cross et al. for robust modular maximization, and we refer to our algorithm as saturated greedy. Basically, following the analysis from Cross et al. And Goyo et al., we prove that our saturated greedy algorithm actually provides a back-criteria approximation guarantee for the problem of robust influence maximization. That is to say, if we are allowed to over-select of the number of seeds by a factor which is log the total number of candidate functions you have, we can then approximate the robust influence within the factor of 1 minus 1 over e plus some small additive error. The interesting part here is actually we can show our algorithm, though it's kind of simple, is near optimum in terms of its approximation guarantee. We also prove a corresponding hardness result for the problem of robust influence maximization and show that this back criteria part is really necessary, as if we are not allowed to over-select the number of seeds by this particular log factor, we show that it's NP hard to approximate the robust influence with any polynomial factor. And this reduction is from the gap version of set cover. Okay. So besides our saturated greedy algorithm, where we have proved this approximation guarantee, we would like to also compare it to some simple heuristics. Though the heuristics don't have any approximation guarantee, the first heuristic we consider is called the single greedy. So though our objective is no longer sum modular, but we can still apply the greedy algorithm on it to obtain a solution, though here without any guarantee. The second heuristic we consider is called O-greedy. Assume that we have k candidate influence function. We just solve influence maximization problem independently for each of these candidates, and then we will get k solutions, and we'll simply pick the solution with the maximum value in terms of the robust influence. Actually, we can construct instance such that we can show these two simple heuristics could feel arbitrarily bad. And one such instance is shown in the right part of this slide. Basically, this instance consists of k candidate influence function, sigma 1 to sigma k, and we assume the diffusion model to be the independent cascade model, where all the existing edge has activation probability 1. For each of these candidate functions, sigma I, it consists of two parts. The left component is a bipartite graph, where we have edges from xi to all the y nodes in the function sigma I, while the right component is the same in all the candidate functions. It's just k disjoint length 2 paths. So now let's see what kind of solution will be obtained by the single greedy algorithm. As for the greedy algorithm, it will try to select the seeds that maximize the marginal gain in terms of the robust influence. Selecting any of these x nodes will contribute nothing to the robustness, because this x node will only succeed in one particular candidate. Selecting y node will, of course, give us a gain of 1. And selecting any of these path head will give us a gain of 2. So the single greedy algorithm will just choose all the path head and just activating all the passes as in all the influence functions. But for any particular influence function, say for example, sigma 1 here, the optimal influence we can get is to select node x1 and any of the k minus 1 node as the path head. That will give us optimum influence of 3k plus m minus 1. So the final robustness, or the robust ratio, will be 2k over 3k plus m minus 1. If we make m much larger than k, this ratio will be much smaller than 1, which means that we get a pretty bad solution for the single greedy. Also, O-greedy doesn't do much better, actually worse. Since the optimal solution for each of the sigma I will be choose xi and any of the k minus 1 node as the path head. But no matter which one you choose, say that our solution, we choose xi plus any of this k minus 1 node here. This xi won't help to activate any of this y node because it works only in one setting. So instead, in O-greedy, we could only guarantee to activate k minus 1 path there and additional node, which is just the xi you choose. Give us a robust influence result, which is also much smaller than 1. But on the contrary, our saturated greedy algorithm, which have this approximation guarantee, will cleverly choose all the x nodes. And then, because all the x nodes are selected, it can guarantee that we can activate all the y nodes. As a result, leading to a robust influence of k plus m over 3k plus m minus 1, which will be approximately 1 because m is much larger than k. And by making m arbitrarily larger, we can make the gap between our robust algorithm with guarantee versus the simple heuristic arbitrarily large. Okay. So though in the previous slide, I showed that there exists instance that we can construct where this heuristic could feel arbitrarily bad, but perhaps they may work in some more realistic settings. So now let's try all the algorithm on some real-world data set. So in our experiment, we use a Twitter data set where each hashtag is treated as a separate cascade. And here, the candidate influence function came from different topics under propagation on the Twitter data set. Basically, we group all the hashtags, namely all the cascades, into 5 categories, leading to a topic of Iran election, Haiti earthquake, technology, climate, and US politics. And in this experiment, we assume the diffusion model as independent cascade model with uniform activation probabilities. The experiment results are all 3 algorithms on 2 Twitter data sets with different number of nodes in the graph, as shown in the lower part of the slide. Here, the y-axis gives the solution of the robust influence by all 3 methods, while the x-axis shows the number of seeds selected by those. 1x means that we select the number of the seeds as required, 1.5x and 2x, which means that we over-select the number of seeds by the corresponding factor. From the result, we can observe that when we are not allowed to over-select the number of seeds, our algorithm, saturate greedy, performs better than the heuristics. But if we are allowed to over-select the number of seeds, say that two more times number of seeds, then all the algorithm gives us a satisfying solution, because here the robust ratio is near 1 or greater than 1. Means that selecting more seeds can compensate for the case that we don't know which candidate function is the actual ground truth one. Moreover, let's take a close look into what kind of seed are actually selected by our robust algorithm versus the algorithm that without this robustness as its design principle. So here we visualize 4 topic-specific networks under the Twitter dataset for topic Iran, Haiti, US politics, and climate. So if we just select our seeds based on the climate network, we may want to concentrate all our seeds within this red ellipsoid, because this is the only dense area in this topic-specific network. But on the other hand, our algorithm will try to hand its best to distribute its node over the dense area in each of these graphs in order to achieve robustness over all of them. And from this visualization result, we can clearly see how the seed selected by our algorithm is more robust than, say, zone influence maximization just based on one particular candidate. So to sum up, as noise and uncertainty is really everywhere in social network data, it really calls for us to take robustness as one of the design principles when we try to solve problems in the domain of social networks. In this paper, we study the problem of robust influence maximization and propose the algorithm saturate greedy to solve it with a back-criteria approximation guarantee. And we also provide a harness result to show that our algorithm is near optimum in terms of approximation guarantee. Moreover, we compare our algorithm to 2 simple heuristics, the single greedy and the all greedy. Though we can construct instances that these 2 can feel arbitrarily bad, but we found empirically they work OK in more realistic settings. In our paper, we have additional results. First is extension to the setting as mentioned in Way's talk. We have result where we have infinitely many candidate influence functions. We have a similar back-criteria harness result for the robust influence maximization under this model, but unfortunately, we still don't know how to solve the robust influence maximization under this infinite case. Moreover, in our paper, we have additional experiment results where the candidate function could come from different diffusion models, different ways that we estimate the parameter of the diffusion model, and also from this perturbation interval model as mentioned by Wei in his talk. Finally, as for future work, the most interesting direction is basically to find the efficient way to find the worst case influence function under the perturbation interval model, which is defined in Wei's talk. Because if we can do that, it will allow us to evaluate the heuristic under this particular model. And more importantly, it will allow us to design this column generation style algorithm to actually solve robust influence maximization under this model. Moreover, we would like to trace a final line between the worst case, which is assumed in our current work, compared to the Bayesian model. Because though here we assume we want to guarantee that our seed works OK even for the worst case. However, the worst case may occur with really small probabilities. So probably we want to instead put a Bayesian prayer over the candidate to express our belief. Finally, as a big picture question, we would like to identify which influence model best captures the behavior of real-world cascade and end-world circumstances. Though our work can help us to mitigate the impact of misspecification of diffusion models, however, it comes at the cost of lowering the performance of each of them. So if we have good answer to this one, perhaps we can make influence maximization more practical and lead to more application of real marketing in real industrial environments. I think that's all for my talk. Thanks for your attention.